All right, so we are still in section 3b. A lot to talk about in this section. And I'd like to look at a couple of other kinds of functions with you here. Actually, it's the same kind, but two different graphs. These next two examples are going to have some fractional exponents in them. And we're going to get a chance to see a couple of things that we haven't seen before. Specifically, what happens when our derivatives are undefined. So here's my first function. And when I look at my first derivative test, f prime would be 5/3 x to the 2/3 minus 2/3 of 6 would be 4 x to the negative 1/3. I'm going to go ahead and, like we started doing in the last examples, I'm going to factor out the smallest power of x, which would be this x to the negative 1/3. I'll get 5/3. And then on my x, notice 2/3 minus a negative 1/3. 2/3 plus a third is just 1. So that's just x to the first, which is really nice, right? Minus 4. Now, this is really an x to the 1/3 in the denominator. In fact, we could even write it that way. And so I'm going to say that if x is 0, this function, or this derivative rather, is undefined. So that makes 0 a critical value. And then I can also say that if 5/3 x minus 4 is equal to 0, I'll get another critical value. 5/3 x equals 4. X would be 12/5. Is 2.4. So two critical values, but they're critical values for different reasons. And I'm going to make that really clear when I create my number line. So here's where we're going to test x equals 0 and x equals 2.4. At x equals 0, f prime is undefined. Well, at 2.4, f prime is 0. This means different things for my graph, right? An undefined derivative is either a vertical tangent line or one of those sharp peaks where they're different from the left and the right. So I'm expecting something unusual to happen here at 0. Whereas at 2.4, I've just got the horizontal tangent line. All right, let's do our test. I'm going to put my first derivative into my calculator. I might as well just use this original one, that's fine. And go to my table. And I'm going to go ahead and choose anything to the left of 0 for a test value. Maybe -1 is fine. In fact, it's already here in my calculator. And I did get a positive value for that derivative. If we choose +1 between 0 and 2.4, looks like our derivative is negative. And then something bigger than 2.4, maybe 3. We're getting a positive. So my graph was increasing, and then decreasing, and then increasing. Meaning that I really do have a maximum here at x equals 0. By the way, this is a fairly simple one. Notice if you go back and plug 0 into the original, you're just going to have 0 minus 0, so 0 for a y value. And I'm also going to mention f prime does not exist here. So I'm looking at an unusual situation, either a vertical tangent line or a sharp point where the graph is different from different directions. I then have a minimum when x is 2.4, and I'll get the y value for that a little bit later. And at that point, my derivative is equal to 0, so there's a horizontal tangent line. That's the one that we've been seeing, so that one's going to look a little bit more normal to me. All right, I'm going to set that aside for now, and we'll come back to that when we're ready to graph. Let's do our second derivative test. F double prime would be 2/3 times 5/3 would give me 10/9. X to the negative 1/3. And a negative times negative, that's a positive 4/3. X to the negative 4/3 for my second derivative. And I'm going to go ahead and follow that same procedure that I've been using. I'm going to factor out the smallest power of x. So x to the negative 4/3 here. That's going to give me 10/9. Negative 1/3 minus a negative, or plus 4/3, would be 3/3, just x to the first. Right, again, just double check. Negative 4/3 plus 1, negative 1/3. Plus 4/3. And again, just a reminder, that's really 1 over x to the 4/3. So if x is 0, once again, I'm going to get this undefined. If x equals 0. And over here, this can be set equal to 0. Oh, let's see, if I multiply by 9/10 here, looks like I'm going to get negative 36/30. It's about, or it is negative 1.2. So once again, I've got two critical values to test. They're critical values for different reasons, although this is not as important to me as it is with the first derivative test. Remember that all I'm trying to figure out is where the inflection points are. So whether my max or my min has a horizontal tangent or a vertical tangent, that's going to change how I draw it. The inflection point, not so much. But let's go ahead and do our second derivative test. Negative 1.2 and 0 are our critical values. The second derivative was 0 here and undefined there. Again, not that that means quite as much this time. And I'm going to put the second derivative in my calculator. 10/9 x to the negative 1/3, going all the way back to here. Plus 4/3, x to the negative 4/3. And we'll try maybe negative 2 would be our first test value, something left of negative 1.2. And I'm getting a negative second derivative. I could try negative 1 in here. Looks like a positive second derivative. And finally, maybe positive 1 out here. And I am getting a positive second derivative again. So I got a change in concavity right here, meaning I do have an inflection point when x is negative 1.2. And again, I'll get the y value in a little bit. No inflection point at 0. Notice that I did not get a change in concavity. This was concave down, concave up, and it stayed concave up after 0. All right, what's this thing going to look like? And I should probably go in and get my y values before I label my y-axis here. I forgot I never did get those y values. Let's do that. If I go back to the original function, x to the 5/3 minus 6x to the 2/3 my minimum was when x is 2.4, negative 6.45. I'm actually just going to round that to negative 6.5. I can't graph all that accurately anyway. And then my inflection point was at negative 1.2. And I'm getting end up about negative 8.1 here. So I need to go down a ways on the y-axis. And let's start marking our points. We have a maximum at 0, 0. And a minimum at 2.4, negative 6.5, around there. We have an inflection point at negative 1.2, negative 8.1. So about there. All right, as I start to graph, bring this up just a little bit. As I start to graph, I want to start increasing but concave down until I reach that first inflection point. So increasing but concave down. I'm going to continue to increase until I hit this maximum, but I'm going to change to concave up. And as I come into this maximum, I'm going to kind of come in with a vertical tangent line, almost vertical right there, right at the maximum. And that accomplishes the fact that at that maximum, f prime doesn't exist. So at the maximum, I'm going to begin to go concave down. Or excuse me, I'm going to go start to increase. Let me try that again. I'm going to begin to decrease, but notice that it stays concave up. So decreasing but concave up. So I come out of this vertical tangent line, concave up, until I hit my minimum. Now this minimum has a nice horizontal tangent line. That's the one I'm more used to seeing. And so it's going to go back up again and stay concave up. And it'll go through the x-axis at some point. Again, at this stage, I'm not asking you to find those points by hand. I know it's going to keep on going up. Maybe I'll just go ahead and look at my calculator graph before I commit to where I want to cross the x-axis. But we have a pretty good idea of what that's going to look like. Let's try it out. We already had the calculator function in there. And so let's see, negative 4 to 4 should be enough on my x-axis, but let's go negative 10 to 4 on the y. And we're beginning to see exactly what we expected here. Now notice, when I drew this, I kind of exaggerated the concavity, concave down and concave up. The calculator shows it almost looking like a straight line. I know it's not, but apparently the curvature there, the concavity, is very, very subtle. So we do know there's an inflection point there, even though it's very difficult to see on the calculator. I actually didn't go far enough out on the x-axis to see where it crosses. Let me change my window one more time. Let's go out to maybe 10 on the x-axis and just see if I can see that. Looks like about 1, 2, 3, 4, 5, right around 6. We're going to cross the x-axis. So in fact, this kind of goes up a little more gradually than I originally started to commit to. And that's what my graph's going to look like. All right, we're going to do one more. We've seen here how sometimes at a maximum, or of course if I turn this upside down, it could have been a minimum. Sometimes at a maximum or a minimum, we can have that vertical tangent line, which corresponds to the derivative not existing. In the next example, we're going to see another example of a derivative that doesn't exist, but it's going to look quite different when we graph it. So I know this is a long section. This is the last graph for this section. Here we go. We've got our function 4x to the 1/3 minus x to the 4/3. And I'll begin again with my first derivative test. F prime would be 4/3 x to the negative 2/3 minus 4/3 x to the 1/3. And I'll follow our now familiar procedure. I'm going to factor out. Actually, I might as well factor out the 4/3 this time. And then the smallest power of x, so x to the negative 2/3. It's going to make that first term just a 1, minus, the 4/3 is already factored out, and here it is again. 1/3 minus negative 2/3 is x to the 3/3, or just x to the first. I could rewrite this with 3x to the 2/3 in the denominator. And I can see again that if x equals 0, that's going to make this derivative undefined. Here, if 1 minus x is equal to 0, then x equals 0. Excuse me, x equals 1. Boy, my arithmetic is going to pot this afternoon. X equals 1. And so that's going to be a critical value where the derivative is equal to 0. So let's test. Zero and 1 are critical values, and this is our first derivative test. At 0, f prime was undefined. So again, I know that the tangent line there is vertical, or at least it's some kind of a sharp point or something. And at 1, the derivative was 0. So that's going to be a horizontal tangent line. We'll do some test values and see what's going on here. I'm going to put that first derivative into my calculator right here. And let's see, I need to start my first test value over here to the left of 0, so maybe negative 1. Gives me a positive value for the derivative. Something in between here, maybe a 0.5. Gives me also a positive value for the derivative. And then something bigger than 1, like for example 2, gives me a negative value for my derivative. So, my function is increasing. It's still increasing. And then it's decreasing. What does this tell me about the graph? Well, at x equals 0, we have neither a max nor a min, right? We didn't change directions at all. But I do have my undefined derivative. So there has to be a vertical tangent at that point, even though there's no max or min. When x is 0, again, just look back up at your function and it's pretty easy to see that y is 0 also. No max min, but the derivative is undefined. So I'm going to remind myself I'm expecting a vertical tangent line there, an undefined slope. At x equal 1, and I'll leave the y value for now, there is a maximum, and this is just a nice horizontal tangent line. Doesn't hurt to jot it down just to remind yourself for when you draw. All right, so that's about all I'm going to get out of that first derivative test. It was quite a bit. Let's do our second derivative test. Starting from here, I would have negative 8/9 x to the negative 5/3 minus 4/9 x to the negative 2/3. And once again, I'm going to go ahead and factor out the smallest power of x, which would be the x to the negative 5/3. I'm going to go ahead and take out the 1/9 also, maybe even a negative 1/9. Just make my algebra a little easier later. So that's going to leave an 8 here. And the minus sign's already out, so a plus 4. Negative 2/3 plus 5/3 would be 3/3, or x to the first again. All right, that's really negative 1 over 9x to the 5/3 times 8 plus 4x. And if x is 0, f double prime is undefined. Here we can actually set the x plus, or h plus 4x equal to 0, which is going to give me x equals negative 2, and that's a critical value. So let's do our test. Negative 2 and 0 are my critical values. And I'm doing the second derivative test here. I know that the second derivative is undefined when x is 0, and it's 0 at negative 2. Again, true, although not as important with the second derivative, because an inflection point is an inflection point, no matter what. And I'm going to plug the second derivative into my calculator. Negative 8/9 x to the negative 5/3 minus 4/9 x to the negative 2/3. And we'll pick some test values. Let's see, I'm going to start with negative 3 over here. Looks like my second derivative is negative. And let's try negative 1 in this middle interval. Positive. And then I'm going to go with positive 1 out here at the end. Negative. So this says concave down, concave up, concave down. Since there is a change in concavity at each of my critical values, they're both inflection points. So at negative 2, whatever the y value is, we'll get it in a minute, we have an inflection point. And at 0, it's also, oh, we already knew that was 0, 0, we also have an inflection point. All right, we're almost there. I'm going to grab these y values, and then we're ready to graph. So one more time in the calculator, I'm now going to put the original function in so I can get y values. That was 4x to the 1/3 minus x to the 4/3. And when x is 1, y is 3. And when x is -2, I get about -7.56. Let's see, I gotta go at least up to 3 and down to about -8. All right. At 0, 0, we have a couple of things happening. It is an inflection point, and I'm also noticing there's a vertical tangent there, so I'm going to label it for myself. It's an inflection point, but also keep in mind when I draw it, it will have to have a vertical tangent line. 1, 3 is a max. And -2, -7.5-ish, up there, is another inflection point. All right, so when I start to draw, my graph should be increasing but concave down until I hit that first inflection point. So increasing but concave down. When I get to that inflection point, I change to concave up. And kind of like last time, I want to come into 0, 0 with a vertical tangent line. So as I come into 0, 0, I'm real vertical. Now here's where it's different. That's not a max or a min this time, it's just an inflection point. So when I leave that inflection point at 0, 0, I'm going to change to concave down. So temporarily vertical, but then changing to concave down to go towards that maximum. So I came in vertical, I left vertical, and then I'm going to come down off the max. And again, I won't commit right now, but I'll have to cross my x-axis somewhere over there. So this will keep on coming down somehow. Right? So there's a vertical tangent that wasn't a max or a min. Let's just finish this one out by taking a look at the calculator graph. Let's see, -4 to 4 should be plenty for x, and -10 to 4 should be fine for y. It looks like I'm going to cross right around that 4 or so when I come down off the maximum, but notice there it is. Again, although it looks somewhat straight, you can just barely start to see there's that concave down part. And then concave up, it's a little bit more dramatic of an angle than when I made it, but you can really see it go vertical in here and then hit that maximum. Doesn't cross until 4 again, so actually my graph's going to come down like this. All right, and there we go. That brings us to the last graph with a function, with an actual formula that we're going to do. We will finish this section by looking at a couple of non-formula given graphs in the very last part.